What is the sound? Ah. All right. So what I want to do today is that I want to sort of go back to those two examples one more time. The we discussed like two cases in distance vector, the forced update and the Poisson reverse. So I want to go back to that example again for two reasons. One is in case somebody wants to look at the videos I'm recording, so it will be there. But more importantly, I think there is a example in your book, and I want to sort of go over that example one more time because I thought like I didn't go into that example in detail in the last class. Okay. So anyway, just to refresh your memory, we were discussing the distance vector protocol in the last class, meaning on Wednesday. So basically we went through this procedure, right? That is a node, in this case, let's say X is the node in which you want to do the update, and it received an update from another node, Z, right? And it wants to calculate the distance to its some other node Y, right? So then it calls this procedure update XYZ, and basically what it does is it computes the new distance as the cost to reaching its neighbor Z, and then the distance to Y from that neighbor dfz comma Y, and then it adds up, and if it turns out to be better, it just updates the cost in the next hop. Otherwise, it just doesn't change anything. It retains the old value. So we saw this in the last class, right? So basically, the basic idea is that periodically every node Z, right, sends each neighbor X, where Z and X span over all the nodes in the tree, the copy of the routing table, and when X receives this table, it simply runs that procedure for every destination Y, right? So at the end of it, it would have figured out how to reach all the nodes in the graph, right? So this process occurs in asynchronous fashion, meaning that whenever it gets the update, it runs this procedure, and the routing tables will eventually converge. So we just to bring the class back, right, to where we were in the last class. So let's see specifically two examples. Okay, these are all things that we discussed. So let's specifically see two examples and see what happens, right? In the first example, let's say the link cost changes, but the cost improves, meaning the actual number of the cost decreases. Okay, so let's take a simple graph, right? XYZ, and let's say the link between X and Y, the cost goes down from 4 to 1, right? So let's see what happens. So what happens is at T0, the node Y, right, detects that the link cost has changed. So its distance to the destination X has changed now, right? It has decreased from 4 to 1. So it knows that, and then it informs its neighbors. And then the message will take some time, and at time T1, after this message transfer latency, Z receives this update, and it figures out, okay, if Y can reach X at a cost of 1, and it knows that it can reach Y at a cost of 1, so it knows its best cost also decreases from 5 to 2, right? And then it updates it, and then it also sends the neighbors its distance vector because the cost has decreased. So in this case, it will also send the update to Y, right? Because it's neighbor. But when Y receives this update from Z, right, it will know that, okay, Z can reach X at a cost of 2, Y can reach X at a cost of 1, right? So what Y has, it's already better. So the table doesn't update and everything is converged. It no longer sends out any messages, right? So the point of this example is that when the cost decreases, when the link becomes better, there's no problem. Actually, the message travels fast, and within one iteration or two iterations, the entire all the nodes converge to the correct answer. So this is good, right? So this is like a positive example. Now let's see what happens when the cost goes up. Okay, so the same example, but let's say the cost of the link X to Y went up from 4 to 60. Okay, so let's consider before the cost change happened, the distance from going from Y to X is 4, and Y to Z is 1, right? And the distance from Z to X is 5, the shortest path, and Z to Y is 1, right? That's what you had before anything happened, okay? And let's say at time t naught, the link cost went up to 60. Now what happens? What happens is that the distance to y from x, right, it recomputes. So the direct link cost is 60, but it also knows that z has an old path of reaching x at a cost of 5. So it, by mistake, tries to reach x through z, right? Even though y is already in the path of z, right? So it creates a loop. And not only does it make a mistake, but it also advertises that mistake back to z, right? Now, when z receives this update at time t1, z tries to reach x through y. So the y's new cost is 6, and it knows that it can reach y at a cost of 1, so it's 7, right? So it also makes the mistake, and then the process repeats, right? Until this dz of x, this equation, this term becomes 50. At that point, it simply stops, right? So basically, starting from 6, right, it goes all the way till 50. So the loop runs 44 times, and at some point, the node z will come to know, hey, my direct link is actually better, right? At that point, it will stop, right? So this is the count to infinity problem, right? This is one of the cases that we discussed in our solution. If you don't have Poisson reverse, meaning the problem here is that, so y should not have made this change, correct? So when y updated the cost, it should have looked at the fact that it's already in the path of z, and it should have suppressed that update. But because it did not, it went into this infinite loop, counting up until one of the thing resolves. But even at that point, you see d of y, right, remains problematic for a long time, right? So this causes this routing loop, right? So basically, when the cost goes up, unless you have these two techniques that we discussed, that is forced update and Poisson reverse, the algorithm sort of goes in a bad direction. It just it goes through an infinite loop for some time. So, any questions? So there are two problems here, right? One is the fact that y wrong updated itself by mistake because it did not figure out that it's on the path, right? So that's one mistake. That's the Poisson reverse. And then we also discussed this forced update, right? So that's the example that we discussed, right? So we discussed we took this graph, which is easier to explain, and then we said, okay, what if this node C fails, right? What if it fails? Basically, the costs will go to infinity, and both F and D will set their cost to C as infinity and iterate, right? And then without any fix, initially it'll go to infinity, but then B had a stale entry, right, of reaching C through F before the failure happened. So that stale entry, right, will eventually propagate to D, right, and D will try to reach C through F, right, C through B, and that update is wrong. And not only that, F, right, will also by mistake try to reach C through B, creating a loop, right? So two problems, right? And then basically we said that, okay, we had two rules, right? One is the Poisson reverse, where if you're creating a loop, check whether the node which is telling you is already in the next hop path, in which case suppress the update, right? And that suppresses the problem for F, because F was already in the best path, right? But it doesn't. So the one thing I want to emphasize here is that the question is that in this case the loop is only formed with two nodes, right? So you are able to compare with the next hop, right, and able to suppress the loop from forming. So the question is, can I solve the count to infinity problem in the general case, where the loop could be formed not just with one node, but let's say spanning 3 nodes. If more than 2 nodes are involved in a loop, right, simply identifying the next hop may not simply fix it. You might have to look at all the nodes in the path and compare whether you are already in the next hop. And if you are, then you'll have to suppress the update. Right? For example, in this case, I'm only comparing the next hop, right? That is one step ahead. But if there are 3 or more nodes involved in the loop, then simply looking one node ahead is not enough. You'll have to look at all the nodes ahead and then compare. So this is something that it's a little bit of a quirk. So in a simple example, the Poisson reverse is always explained with only one next hop, but in a general case, you'll have to sort of compare with all the nodes in the path. Any questions? Okay. And then we also discussed this post update thing. That is, when there is a cost change, and if you're already affected by the path, then you'll have to go and make that change. Specifically, for example, if the next hop going from X to Y is already Z, and then if you get an update from Z, right, even if that update is increasing the cost, you'll have to still update it because that's the only viable path that you have, right? So basically, we saw this example, and then with forced update, we are also able to. So basically, initially the stale entry of B propagates to D, right? In this case, because D falsely assumes that it can reach the fail node C going through B, right? But then, if you have forced update, what will happen is that ultimately B will go to infinity, right? And then at that point, because of forced update, right, it will force D also to go to infinity, right? You see here why B went to infinity, right? Because when F advertised infinity at some point, and then when B gets that message, B will be forced to update its cost to infinity because of forced update rule. And then once it updates the cost, it will obviously advertise that to D, and then D will force its cost to infinity. So with these two fixes, sort of we saw how this example converges. So that's something that we discussed. I'm just saying to refresh the memory. Any questions? Okay, hold on. Okay.
So B will first falsely tell F that it has a better path, then F runs the algorithm.
So B does not tell falsely. It's just that B stale entry, right, propagates.
Correct.
Yeah.
Stale entry will go to F, then F will check if it is the next hop, and then tell B that the actual cost is infinity. And that's how D comes from B.
So D made a mistake, right? Because the stale entry from B, right, went to D.
Yeah.
So D falsely updated it to 5, right?
Yeah.
That happened. And then, but ultimately, this infinity for B will happen because when F goes to infinity, right, it will advertise that. Like basically this entry, and this entry, right, when it reaches, it will be forced to update.
So if you're updating, will it try to find another path?
No, if it exists, but in this case, there's no path that exists. Yeah, if it exists, it will. But in this specific example, the entry, if you focus on the table entry for B, the leftmost thing, so its cost went to infinity because if you compare the next hop entry for that, it's through F, right? So when it receives an update from F, it will be forced to make that cost infinity. because of this forced update rule. And once it makes that cost to infinity, it will be forced to announce the update because the cost changed. And once it announces the update to D, right, look at D's entry before the update. Its next hop is B, right? That means that any advertisement from B, it will be forced to apply. Did that make it clear? Okay. Any other questions? So I think there's two rules for distance vector along with this example. This is important. So I think you guys should understand it very clearly. All right. I just went through this again simply because this is a little bit important. Okay. All right. So let me